Welcome everybody this morning at 9 o'clock to this lecture by Professor Julio Fernández from the Department of Astronomy, Montevideo, Uruguay. And I think almost everybody knows Professor Julio Fernández because he has written this famous paper in 1980 on the origin of Kuiper belt. I should say that if I'm correct, I believe that you did not even mention Kuiper belt in your paper, but you just talk about something outside Neptune, right? Yeah.
Yeah, yes. Transneptunian belt.
Yeah, and then he was in Madrid at the Madrid Observatory, and then he went to the Max Planck Institute for Aeronomy in Lindau, Germany, to work as a postdoc, and that is where I met Julio, and we have cooperated a few years, and I would say rather fruitfully, on the dynamics of the outer solar system, especially on the orbital migration of the outer planets, Neptune and Uranus. And since then, he had. And he spent another few years at the Max Planck Institute. Am I right? Heidelberg. Then eventually he returned to Uruguay as a professor at the university, and he became very productive and producing very excellent papers, results, and also start building up a group in small bodies in Uruguay, and which has been very influential, in IAU, I would say, yeah. I think you are the one who is partially responsible for downgrading Pluto. Am I right? So, and he's going to tell us about his view on the past, present, and future of the Transneptunian belt. It should be a very interesting talk. Julio, please.
Well, good morning to everybody. Thanks, Wing, for your kind introduction. Well, okay, as you have mentioned, I have been working on the Transneptunian belt since long time ago. No was, of course, my only topic. I then devoted much of my time to comets, and then went back to the Transneptunian belt. Well, I think that really it's a very challenging subject. In this talk, I would like just to give a summary of the story of the belt from the beginnings, when a young astronomer that was hired at the Lowell Observatory started the search of planet X, a planet that was hypothesized by Percival Lowell, and with dose of luck, he discovered this planet less than 1 year later, in 1930. This young astronomer was Klein Tombaugh, that became a very well-known astronomer. Well, the interesting thing that was that Pluto was hailed as the ninth planet of the solar system. It was interesting that at the beginnings, people speculated that Pluto was a rather big planet, perhaps even with a size similar to the Earth. But later on, observations, we can just mention a few then. One key observation was carried out by Gerard Kuiper in 1950, showed that Pluto was is much smaller than the Earth. This is the number 2, the measurement of the size of Pluto by Kuiper. And then other measurements show that Pluto were indeed much smaller than thought at the beginning. We now know that it's more than almost 10,000 in mass smaller than the Earth. Then it's actually smaller than the Moon. The mass of Pluto could be determined when Charon, its satellite, was discovered in 1977. Then by dynamics, it could be determined the mass of the system. Well, then the discovery of Pluto triggered discussion, speculations about what if there beyond Neptune there was more bodies, and what was the reason that we found planets there, and if more planets could be discovered there. And then the idea were that if the solar system formed in a protoplanetary disk where planets formed and accreted mass, then there was no reason to think that the solar system ended abruptly at Neptune's distance. Then it was natural to think that the matter was distributed even farther away from Neptune, and perhaps not the large planets could form at larger distances, but smaller bodies like Pluto could form in the Transneptunian region. There were several authors, as you see, Edgeworth in the first place, Kuiper, Cameron, Whipple. It is interesting that Whipple tried to estimate the mass of the comet GreenNobel beyond Neptune, just considering perturbations in the orbit of Halley's comet. The Halley's comet goes in its aphelion right in the zone where the Transneptunian belt was supposed to be. And then the first estimate of the mass of this putative ring or belt was given by Whipple and put the limit at about 0.5 to 1.3 Earth masses, dependent on its location. Well, then there was an interesting aspect that relates the Transneptunian population with comets. And the thing was that Jupiter family comets was a puzzle, how if they were related to long period comets, if they were coming also from the Oort cloud as the long period comets. There were difficulties just to think that Jupiter family comets could have the same origin as long period comets. There were essentially two main objections. One has to do with the so-called Tisserand parameter that is given by this expression, and is a quasi-invariant in the three-body problem. In our case, the three bodies are Jupiter, Sun, Jupiter, and the comet. The Tisserand parameter gives then an idea about where the origin originated. What we can see, this is a plot of comets, of those are comets with perihelion distances smaller than 1.3 astronomical units. That is, these are comets that approach across Earth's orbit. And you can see that Jupiter family comets are there. This is a plotted Tisserand parameter versus the energy of the comet. And you can see here that the Jupiter family comets in red dots are the ones with the stronger binding energy and occupy the region with Tisserand parameters essentially between 2 and 3, while long period comets and also Halley-type comets have Tisserand parameters smaller than 2. And then there is a clear distinction between two populations. The other objection to the hypothesis that Jupiter family comets should come from the evolution, dynamical evolution of long period comets, is that the capture efficiency was found to be too low, and then an estimate gave a factor of 40,000 too low to keep the Jupiter family comet population in a steady state. Then at that time, I started to see in the problem, and then just to simplify matters, I asked the question to myself, why not to assume that Jupiter family comets come from a flat Transneptunian source? And this was the origin of my paper that Wayne mentioned of the year 1980. Well, then the paper developed the idea that Transneptunian bodies could be perturbed by Pluto or moon-sized bodies that could be present in this region, and then these weak perturbations were enough just to push some of the tnos to the Neptune sphere of influence, and then be scattered by Neptune, and then some of the objects could be scattered inwards to the inner planetary region, and others ejected to interstellar space. In my own calculation in that paper, I found that 0.006 of the comets were captured in Jupiter family comet orbits. And this, even though it's a small number, is still 2 or 3 orders of magnitude larger than that derived from direct captures of Oort-Cloud comets. There were, after my work, numerical simulations taking advantage of the increasing capabilities of computers to do the massive numerical simulations, and then in other works, the efficiency of capture of Transneptunian bodies in Jupiter family comet orbits was found to be of about 1/3 of the scattered bodies. One byproduct of the transfer of body from the Transneptunian belt to the Jupiter family comet region was that there is a transient population in the outer planetary region that we now call centaurs. And this, of course, many of these objects have been discovered Well, then just to illustrate you how is the procedure. That is, if comets are originally in a Transneptunian belt, some of the objects are moved inwards and they get under the gravitational influence of Neptune, and then Neptune in this sketch scatters some of these objects to inwards, and some of them reach the orbit of Uranus, as we can show here, and then the evolution can continue for some of the objects in the following way. From Uranus, it handed down to Saturn, from Saturn to Jupiter, and then from Jupiter is sent inwards and the object become a Jupiter family comet. Well, then when there was with the development of computers that were capable of doing more massive numerical simulation, there was a renewed interest in simulating the dynamical evolution of bodies in the Transneptunian region. And there was some works that could produce maps of this region, the Transneptunian region, showing regions of dynamical stability and other regions that were dynamically unstable. What was found was there was a substantial dynamical erosion. Here you can see here in these simulations by Holman and Winston, this originally was a population of bodies that was just scattered along the planetary region up to distances of 50 AU, and then we can see that in the region among the Jovian planets, bodies, the population start to decrease very, very rapidly because these are essentially dynamically unstable regions. But then we have here in the Transneptunian region that there are some regions that are stable for the time period of the simulation that was 100 million years. Well, that was then studies from the dynamical point of view, essentially were numerical simulations. But around the year 1990, the situation was ripe to start new search programs of other Transneptunian objects besides Pluto and its satellite Charon. Well, then, as actually happened, 2 years after that, in 1992, Hewitt and Lu discovered another TNO that was called 1992 QE1. Now it's called Albion. And what we can see here is that the discovery rate, that is when you discover one object, then you have others that follow, and then because other observers also jump into the game, and then many people start to get enthusiastic about that, and then the discoveries proceed at a faster pace, and we can see that thanks to several survey programs, there were discovery of large number of tnos until now that the number exists is greater than 2,000. Well, then we have by now a number of tnos that is large enough to start to classify them from a dynamical point of view. The classification that has been done and accepted by most researchers that give a group, the so-called the classical tnos, that are characterized by low eccentricities, smaller than 0.25, and semi-major axis in the range between 41 and 46 AU. That is, these are in a ring around the sun, a rather flat structure. Then we have the resonant tnos. The resonant are mean-motion resonant with Neptune, could be the 1, 2, 2, 3, 3, 4, 4, 7, 2, 5, 1, 3, and several more. These are the most crowded ones. In particular, 2, 3 is where Pluto is located, and for this reason, the bodies that are in the 2, 3 mean-motion resonance are called Plutinos. Then we have the scattered disk population, that they have the perihelion distances between 30 and 40 AU, semi-major axis greater than 50 AU, and finally we have the detached population. These are with perihelion distances greater than 40 AU, that is, they are quite far away from Neptune, and the semi-major axis are greater than 50 AU. Okay, here we have in these plots inclinations, as you see, versus semi-major axis, and eccentricities versus semi-major axis. These are well-known plots of the Transneptunian population. Well, then one aspect, an interesting aspect is that we can distinguish two classes of population from if we just consider not only dynamical aspects but also physical aspects. We have the so-called cold population, that is the one located in the classical disk, that has inclinations smaller than 5 degrees, and they are characterized for having red colors. We found among the TNOs in the cold disk a larger fraction of white binaries. And then we had the hot population, what is composed of the objects TNOs in the classical disk, in the scatter and in the resonances, and that have inclination greater than 5 degrees. They are characterized from a physical point of view to be more neutral, to have more neutral colors, and they also show a smaller fraction of binaries. Then we have the question, the interesting question is one of the topics that are now hotly debated, if cold classicals form in situ or were transferred from inner regions, from the inner regions of the solar system. And what about the hot population was implanted from the inner region? It seems that the hot population was implanted, and in that case could be a fossil record of planet migration. We're going to talk about planet migration in the next slide. And then we have the cold and the hot disk in the Transneptunian zone could have different origins. The cold disk be primordial and the hot disk be implanted from inner regions in the planetary, in the solar system. We're talking about planet migration from numerical simulations that we carried out with wind decades ago. We found that the accretion of the Jovian planets was not only a process of mass accretion, but also involved the motion of the planets, the displacement of the planets from their original locations, in such a way that Jupiter, for instance, we found that Jupiter moved slightly inside, whereas Saturn, Uranus, and Neptune moved outwards. And this is something that now is widely accepted, that planets, the Jovian planets, during their accretion process migrated. In particular, Neptune is very important for the Transneptunian disk, because Neptune, in its motion away, outwards, will just drag many planetesimals that were trapped in resonances with Neptune and move outwards with the planet. Then it was possible that if there was a lot of matter in the region of formation of Neptune, about 25-30 AU, then some of the matter that was moved outwards as Neptune migrated could have been placed in the Transneptunian zone. This was modeled by Nesforny a few years ago, and actually the process is not very efficient, but he found that about 20 Earth masses is required just to place the right amount of matter in the hot disk of the Transneptunian region. Well, here we have several problems, of course, that I think that this is an open problem, because the migration of Neptune and the emplacement of matter in the Transneptunian region implies that the matter, at least in the planetary disk, ended at 30 AU because Neptune had to stop the migration, and to stop the migration, then the matter cannot be matter far away, because then Neptune will continue in migration outwards to larger distances. Well, then We are going now to talk something about the size distribution, the total mass of the Transneptunian population. Of course, these are preliminary studies because we don't have a good range of sizes for the discovery tnos, and then we have just to rely on some extrapolation and some bias. We have to take into account different bias. But now the estimate, one interesting thing is that both population, hot and cold population, have similar size distribution function, but with slightly differences. For instance, they both are bimodal, at least in the range of absolute magnitudes that have been studied, but the bimodality changes, the slope changes at different values for the cold and hot populations. Okay, if we have an idea of the size distribution and we have some estimate of the population of the largest TNO and extrapolate to smaller sizes, we can make an estimate of the total mass of the Transneptunian population. Doing this calculation, we found that the mass of the hot population is about 1/100 of their mass, whereas the mass of the cold population, that could be a relic of the early protoplanetary disk, or namely a primordial population, is only 3 times 10 to the minus 4, that is 30 times smaller than the mass of the hot population. An interesting thing is that all large TNOs, what we call now dwarf planets, belong to the hot population, like Pluto, Eris, Makemake, Haumea, to mention the most well-known TNOs, Charon. But of course, it's also interesting to know about the size distribution at the lower end, because there we have the comet size TNOs, and these are important because they are, as we believe, the source of the Jupiter family comets. That is, there have been some projects to try to estimate this population. It's difficult, not to say impossible, just to observe TNOs with diameters smaller than 100 kilometers. Then we have to rely on other methods, such as the occultation of stars by TNOs, and then you have here at your institute the TAOS project. But now they have been possible to do crater counts by the New Horizons spacecraft on the surfaces of Pluto and Charon. And then when we show the crater diameter that can be transformed into size of the impactor, namely the small TNOs that collided to produce the craters, then we have there is a population of impactors that goes with an exponent about -3, and then there is a rapid fall off for smaller crater diameters, smaller than about 30 kilometers, and these are produced by impactors with dimensions, diameters of 1-2 kilometers, that are right the dimensions of comets. The typical comets that we observe have this dimension. Then this suggests a paucity that small tnos are really very scarce. And then we have from these studies just to evaluate if the population of small tnos is sufficient to feed the inner planetary region with Jupiter family comets. Well, of course, other important aspect is the size and albedo of the tnos, and we have visual albedos and versus absolute R band magnitudes for the hot objects that are the red triangles and cold objects blue squares, and we have here how they are located in this diagram. Well, we cannot say too much. There is actually albedos for hot and cold objects are more or less well mixed. There is not a clear trend, but we observe that the objects with the lowest absolute magnitudes, that is the brightest objects, are well detached from the rest of the population with very high albedos. And this is due to these objects are large enough. We have here Pluto, Eris, among all the Makemake, I think Sharon. This is indicating that these are massive enough to be able to trap gases that form transient atmospheres, and then these atmospheres, the gases cool down, and they just deposit on the surface again, forming a thin layer of frost of methane and nitrogen. And this is the reason why these objects have so high albedos. Another important aspect of the tnos, going to the physical characteristics, is the rock-to-ice ratio in these bodies. We know that they have both rock and ice, and there are some differences in the proportions. Some of the bodies seem to be rockier, another icier, and there are also differences, clear differences in the bulk density. We can see here in this diagram the bulk density versus diameter. Here are the smaller tnos. These tend to be of smaller bulk densities, whereas the objects, the largest objects, have greater bulk densities of 2.5 grams per cubic centimeter. Well, they have to do, we can just invoke two reasons for these differences in the bulk densities. One could be a different rock-to-ice ratios, and the other is different porosities. The fact that large tnos show different bulk densities suggests different rock-to-ice ratio. This is clear. But there is also we can see here that the smaller tnos show very small, very low bond densities, and this has to be for sure with different porosities. That is, these objects are very porous, whereas more massive TNOs, because of their larger gravitational fields, they compress the material, crashing the pores and then becoming just a continuous material, a porosity-free material, and then the density is that typical of a mixture of ice and rock that is about 2 grams per cubic centimeter. Well, then the reason that some of the oceans can have the different rock to ice ratios could be due to mega impacts. The impact between two large TNOs can just strip the larger TNO of icy material that forms the mantle and leaves intact, or at least the largest portion of the rocky nucleus, and then we give to the body that remains after the impact with a larger composition of rock with respect to ice. Then this could be one of the reasons that explain why some of the large TNOs seem to be rockier and others icier. Well, New Horizons mission show that the Pluto-Charon system has some regions are young due to extensive resurfacing, but there are also old regions with positive craters with diameters smaller than 30 kilometers. I talked about this before, and this indicates that the population of small TNOs is smaller than could be theoretically predicted for a mere extrapolation of the size distribution from larger surfaces down to kilometer size. What is interesting and intriguing and very challenging speculation is that Pluto and also Charon, because they have such two tides, could have for sure an icy mantle, but also they could have a part of the ice in liquid state, and then they might be provided of interior ocean, as we have observed for other bodies like Enceladus, that they have geysers and other phenomena, geophysical phenomena like geyser and cryovolcanism. Of course, this is a very interesting topic for astrobiology. Well, we have the New Horizons also visited a TNO, a simple, very, very common small TNO. Was at the beginning called Ultima Thule, and then later on they received the name of Arrokoth. And then it's very interesting because we found a TNO that is the fusion of two pieces, and this could be produced by the formation process in which the body accreted material giving rise to two bodies that were moving around their common center of mass, and then due to ties that finally merge, forming this curious object. Well, then we have just going to finish, because I have a few minutes. We have interest in the detached population, how objects TNO can be detached from Neptune, and then here we have that there are dynamical mechanisms, in particular the cosine mechanism can rise the perihelion distances up to 70 astronomical units, and that might explain why many of the bodies we observe in the detached population have so large perihelion distances. Of course, there are objects like Sedna that have perihelion distances greater than 70 astronomical units, and then this perihelion distance cannot be explained by the cosine mechanism, and then it is possible that there are objects, these are simulations, that they scatter from due to Neptune perturbations outwards, and they get in successive passages larger and larger semi-major axis until they fall under the perturbing influence of the galactic tides and passing stars. And then these perturbations can rise their perihelia, and actually these objects become members of the inner Oort cloud. And then we have that Sedna, for instance, can be a member of the inner Oort cloud, because very likely, because of its large perihelion distance, it suffers the perturbations of some passing star. Well, one of the challenging topics that is now being studied, at least there are people who try to discover what has been called Planet 9, and the rationale for the existence of Planet 9 or a large planet in the Transneptunian region between the Transneptunian region and the Oort cloud is because, as we talked before, the accretion process of the Jovian planets led to the scattering of a large number of planetesimals with a mass, total mass of several Earth masses, and then we can see that one of the scattered objects will have the mass of a planet like the Earth or Mars or something like that. Well, what are the facts? There was an alignment in the argument of perihelia of distant TNOs with semi-major axis greater than 150 astronomical units, and this was attributed, this alignment of their argument of perihelion, to the presence of a distant planet. Yet, the discovery of other, of more distant TNOs showed that such an alignment didn't occur, and then we can say that there was just a result that was just based on very few objects, a too small sample, and then one thing that we have to bear in mind is that we cannot trust on small number of statistics. That if we need a larger sample of distant TNOs to check if they are really have some clustering around an orbital parameter that might be due to the presence of a massive distant planet. Okay, just going to the end of my talk, I will just give you a summary of some of the important aspects that are now being discussed. Are really very exciting. I had to do not only with the Transneptunian bed in itself, but also with the origin and evolution of the solar system. When we have points like the discussion about the Transneptunian bed, what was the in situ formation versus implantation, what is the proportion of each one of these contributions. Other aspect has to do with the different rock to ice ratios that or that also can be due to different porosities. Then the existence of planet 9, the binary formation, why is different the proportion of binaries in the hot and cold disk. Then the existence of cryovolcanisms and also the interior oceans. Something that is also interesting is that if there is a cutoff in the distribution of TNOs at the 1.2 mid-motion resonance, that is semi-major axis, correspond to a semi-major axis of 47.7 AU. And finally, I would say that it will be very interesting just to define what is actually the actual population of comet-sized TNOs, because these are the source of the Jupiter family comets that we observe. Okay. Finally, thank you for your attention. And if there is some question, where I will be happy to try to answer it.
Yeah, thank you so much, Julio. So, any question from the audience? First, please, raise your hand or just turn on your mic. Zhongyi Lin, you have a question, please.
Yes. So Julio, so I have a question about when we say we have detection for the WAS. You say the WAS dust ice ratio means we have been detected the water sublimation rate, or we have detected the water production rate from those TNO. Or I mean, how do we get the dust to the ice ratio from those TNO, since they're very, very small?
Yes, that is, this is a good question. Of course, we don't have now refined models of interior. The data we have are for some objects we have the mass, because they are in binary system and they can determine the mass of the system. And we have the size, because of this object we have determined the the size through the observation of transits, occultation of stars by these objects. And then we have the bulk density. What we have for the large objects, Eris, Pluto, Charon, look at the one that you observe, you see here, Makemake, Haumea, that they have bulk densities that are different among them. And there are about between 2 and 3 grams per cubic centimeter. And then the only explanation that you have is that the proportion of ice to rock is different for these bodies. I don't know if the explanation was clear.
All right. There's a question in the chat box from Professor Leon Zhao from Nanjing University. Can you hear me? I mean, the question is,
yes.
Thanks for the very interesting talk. Could you please comment the possibility of those detached tnos encountering with nearby stars on their way out to Oort cloud?
Yes, yeah. That is. We did simulations, and yes, there is encounter of scattered tnos with passing stars occur in a statistical sense. That is, you have that. If you take a time span of 1 gigayears, you have many stars that pass to some tens or thousand or tens of thousands of astronomical units from the sun. And then you will have that these stars perturb comets in their way out or in. That is, there are scattered these objects that are far away.
Well, there's a massive simulation paper by Akira Hikuchi and Takahashi Ito, but that hasn't been published yet. But that includes some of this process here, so it should be very interesting for you to take a look.
Okay.
Yeah, right, Julio. I think you are the reviewer. There's a question from Lin Qihong. Qihong Lin, you raised your hand. You want to ask a question?
Oh, okay. So, good morning, Professor. So I have a few questions for you. So the first one is because you mentioned about there is one ocean, so it is under the shell of the Pluto. So my question is, if this ocean is around the core of Pluto, so that means
the connection is not good.
Hello?
Yeah, but I understand that is. I am listening.
Okay. So the core,
the inner ocean.
Yeah. So this means this core, this is suspended in liquid. So when is that possible that the satellites of the Pluto, the Charon, their gravity effect, they will be shaking this core under the shell, because this core was free. There is no fixes by the rock by the shell. So is this the core will be shaking since the ocean inside, or make this Pluto has something strange effect? So that is my first question.
That is regarding the ocean. There are no proofs that the ocean exists. That is at this moment it's a speculation. That is, there are some young regions, geologically young regions in Pluto and Charon, that could be due to the presence of cryovolcanisms. But this is not a case like, for instance, Enceladus, that we observe now activity there. That is, we we don't, at this moment, we just only speculate that can be in some objects, inner oceans, but we cannot just prove their existence.
Okay, so my second question is because we know there is many tiny objects, the TNO or KBO. So this is in the Oort cloud inside use the high eccentricity orbit, so around this the sun. So my question is because we know this kinds the tiny object, it has a very long period, but every time, but it still has enough gravity. So my question is when this kinds of objects and every time they are flash into they are moving to the orbit cloud and moving out, moving, so can it cause any effect, gravity effect for the tiny rock, tiny asteroids in the orbit cloud inside, because maybe something rock comets, they are moving into the inner solar system. So like for example, maybe it's a asteroid that's to extinct the dinosaurs is come from this kind of the dwarf planet gravity effect. Is that possible? So this is my second question.
I try to understand that is you if objects coming from the cloud,
yeah,
that is if they can collide with the Earth and causing extinctions of dinosaurs, mass extinction, something like that. This is part of the question. The probability of a collision of a comet coming from the Earth cloud with the Earth is very low. There are other bodies that have a greater probability of collision with the Earth. For instance, Jupiter family comets or asteroids.
Okay, so my last question is because just like you say, there is something has something organic chemical material like the CH2 or N2. This kind of material, maybe this is a coated in this the TNO surface. So my question is because this kind of TNO, the gravity is very low, and there's no atmosphere, and there's no enough the magnetic shield to protect them. So how this kind of organic chemical material to stay in this TNO surface and don't to break down by the radiation come from the universe or sun? So this is the last question. Thank you.
Well, that is, you have the surfaces of the TNOs. Yes, you have frozen nitrogen, frozen methane, and other hydrocarbons. These ices are subject to cosmic radiation, cosmic rays. Well, there are chemical reactions and they form more complex organic compounds and what is called the red or ultra-red material in their surfaces. That produce a change in the color that is observed in some TNOs. Of course, you have a process, a competing process of gardening because cosmic rays act on the ices and form organic compounds, but then you have collisions by micrometeorites, and then this produces a gardening, and this the material is renovated, and then you have there two competing processes. And then you have that some TNOs can be more red and others can be of more neutral colors.
Okay, a quick answer to this question is, I mean, according to the Rosetta mission to comet to remove Gerasimenko, what we find is that the comet is made up of ice, of course, water ice and CO2 and so on, and solid dust particle. What's interesting is that the solid dust particle are made up of hydrocarbon material, organic hydrocarbon material. So in fact, the whole thing, the whole complex, presumably also the Transneptunian object also make up of organic materials. So there's no problem at all. So the question is to say that how did then the organic materials generated or formed in the aerosol system? So there's another good question, but I think that that we have to consider that, to discuss that later in another talk perhaps. Okay, I think that we have taken up Julio's too much time. It's already 10 minutes past 9 o'clock, right? 10 o'clock. So if there are no other questions, or if you have questions, you could write to me, or write to Julio, and I could pass. If you write to me, I could pass them to Julio, and I'm sure that he will be very happy to answer you. And thank you. And I hope to see you. I hope to be able to invite you to visit Taiwan very soon. And then I'm happy to see you healthy, and dynamic as usual. And keep it up. Yeah, keep it up.
Okay.
Yeah. Thank you.
Thank you again. Thank you again for the invitation.
Yeah.
And goodbye. And I hope to see you very soon.
And I told Diana that you'll be giving a talk, and she might be even watching you. Yes.
Okay.
Okay. Bye bye.
Goodbye.
Yeah.
Bye bye.